Yeah, so today I'll be giving an update on our mission Lunar-VISE, which, as a reminder, is the Lunar Vulcan Imaging and Spectroscopy Explorer, which was selected as part of NASA's call to go to the Gruithuisen domes. And we are now a part of Task Order CP21, where we're going to have a 10-day surface investigation, a 10 Earth Day surface investigation, to really understand the formation of silicic volcanism, in particular at the Gruithuisen domes. So we have one overarching science goal, which is to understand how lunar silicic volcanism works as typified by the Gruithuisen dome. And then we're going to take what we're learning in situ at the Gruithuisen domes and apply that to other silicic volcanic constructs across the lunar surface to build a better understanding of silicic volcanism as a whole. We also have an exploration goal, which is to understand the geotechnical properties of the regolith at the Gruithuisen domes, and we're going to do that by looking at any variations that we see across the dome as we're roving about. To conduct our science investigation and to really understand the composition making up the Gruithuisen domes, we have two main payloads. We have the LV-GRNS, which is a gamma ray and neutron spectrometer that will sit on the backside of the rover. And then we have two multispectral cameras, LV-VIC and LV-Cirrus, that sit in a single enclosure on top of the rover and are bore-sighted and have the capability of doing 180-degree panoramic scans as we're getting to our stations and looking at boulders and regolith. If we assume that our instruments are at a height of 1 meter off the lunar surface, that means that at 3 meters away from us, we'll be getting sub-centimeter spatial resolution of anything that we're viewing. To map variations in composition across the dome, the first instrument that we'll be using is LV-VIC, or it's our multispectral visible near-infrared imaging camera. LV-VIC has 7 spectral channels, which are shown here in the chart. And you can see that these are fairly familiar looking spectral channels because these are channels that have flown in orbital data sets. And so these liken back to Clementine data, LROC WAC data, Kaguya. And so any measurements that we make at the surface will be able to link to all the orbital data sets that we have in hand. And in particular, what LV-VIC is going to be looking for is any variations in mafic mineral abundance across the dome and constrain how much iron we're seeing across the dome. And we can do that by looking for variations in this 1 micron band that we can see here in some of the most common lunar minerals. And these lab spectra have been resampled to our VIC bands to show what we will be seeing at the surface. We'll also be using LV-Cirrus. And LV-Cirrus and LV-VIC, again, are co-bore sighted in a single enclosure. LV-Cirrus is similar to L-Cirrus, which is a thermal infrared camera that will be going on CP22 to the south pole of the moon. The main difference between L-Cirrus and LV-Cirrus is our spectral channels, and that for LV-Cirrus, we have optimized our spectral channels to be able to map compositions that are very silicic in nature. And so those are shown here. These are channels that are also being flown on Lunar Trailblazer and also overlap with some of the Diviner channels. So we'll again be able to make that link between our in situ observations and our orbital data. These channels have been specifically chosen to map the CF feature, which gives us silicate composition, which you can see here on the plot where on the y-axis we're looking at the Christensen feature position, and on the x-axis we're looking at silicate composition. And this is for lunar samples, both mare and feldspathic materials, as well as some very silicic materials. And we see this nice correlation between CF position and silicate composition that again we'll be able to use to map composition across the dome. We'll also be using a wide range thermal imager, or a wide range thermal channel that will also allow us to map composition, or sorry, map temperature across the dome. Having problems here. Yeah, so we're gonna use the wide range thermal channel to map temperature across the dome. And by making observations of rocks and regolith at multiple times of lunar day, we can build diurnal curves up of these materials, which will allow us to estimate thermophysical properties like porosity and thermal inertia. And again, this will help us build an understanding of how these volcanic constructs have formed. To highlight some of our hardware that is currently being built, I have some images if they'll come up. Yeah, so here, just to highlight a few of our hardware pieces, we have the LV Cirrus block filters, showing our 4 filters here. We have a scene select mirror assembly, and then we're showing here our calibration sources that we'll be using. Also on the rover, we have our gamma ray and neutron spectrometer, which is built with 2 different sensors. We have a gamma ray sensor, which is a 2.5-inch cylinder click sensor, and then we have a 2-inch diameter click sensor that is for the neutron sensor. And we can see these over here on the left. On the right, what we're showing is a model gamma ray spectrum using specifications of our click sensors. And this green line is showing what a modeled gamma ray spectrum would be for a 4-hour integration, which is what we're expecting at the surface. And using that modeled or calculated gamma ray spectrum, you can see that we will easily be able to identify thorium as well as uranium and potassium, and also look for other silicate or things like iron and silica and hydrogen. Also, to showcase some of our hardware here. So here on the left are the gamma ray and neutron sensors. So in the front are the neutron sensors, which again are 2 inches in diameter. On the left, we're showing the electronics exposed. On the right, we have the electronics closed off. In the back, we're seeing the gamma ray sensors.
3 minutes.
And then on the right, we're showing the GRNS radiator and the heaters that are bonded to it to keep it nice and warm throughout the mission. To conduct our exploration goal, we have 2 cameras on the lander. We have a descent camera that will be nadir pointing as we land at the surface. And then we have a context camera that will sit and have the capability of doing 270-degree panoramic scans of the area. Using these 2 cameras, we'll be able to image the landing site to help us select a rover traverses and characterize the surface pre and post interaction with the lander. And then we'll also be able to use the camera to watch as the rover is interacting with the regolith. And so this will really allow us to build up an understanding of the geotechnical properties of the domes. We have selected our landing site on the Gamma Dome, which you can see here in this image here where we have this green box. And this is a zoomed in version of that green box. We have our landing site here with our 100-meter diameter landing ellipse. And then we have now selected 6 stations away from the landing site that will allow us to accomplish all of our science goals. And so we've selected sites that give us easy access to boulders and regolith, as well as views out to the mare surrounding the dome. And so to highlight a few of those, here are some of the waypoints where we have access to multiple undisturbed boulders and regolith. So these are stations 1, 3, 4, and 5. And here are zoomed in views of those. And you can see that we should easily be able to approach any of these boulders and really move around them and get good images at different times of lunar day, as well as at different sun angles, which will give us composition and thermophysical properties. And then here's just a viewpoint that Ernie Wright from NASA Goddard was kind enough to do for us. And so this is showing that if we were at Station 2 and we were looking out to the mare below, what our viewpoint would look like. So indeed, from our location, we should be able to get nice observations of the surrounding mare, as well as potentially the Delta Dome, depending upon where we're able to access. So just to kind of wrap up, We are currently, this is where we're currently at. So we have successfully passed CDR and KDP. All of our instruments are currently under development, and individual components and assemblies are undergoing functional and performance testing. We're on track for an on-time delivery in place in August of 2025. And as a team, we're working to continue and refine our notional design reference mission to really get the most science that we can while we're at the surface. And I'll just end here highlighting some of the presentations the rest of this week by graduate students that are working on the Lunar-VISE project. So Zach Fig will be giving a talk this afternoon, and then we have 2 poster presentations tomorrow evening by Elena Dolgus and Sean Burnett. Thank you.